Okay, welcome everybody. This is Graham Carter, and I'll be moderating the session today. So thanks very much for joining us. If I can just hand it to our friends from ED2.
Okay, thank you very much, Graham. Good morning or good afternoon to everyone out there. My name is Joel Blumke. I'm the VP of Engineering here at ED2. We're going to be talking to you today about 5G millimeter wave repeaters. So jumping into the agenda, I'm going to do a brief description of who we are, a little bit about the differentiators, and then talk about some basics. Then Marwan's going to get into some of the use cases and why we want to use 5G millimeter wave repeaters. And then Kevin's going to dive down into some of the technology that we're using here to make our repeaters. The goal here today is to share as much as we can without getting into an NDA situation. So hopefully we're going to present something that's going to be a little bit different for you guys. So we're basically an emerging company. We're located in Tucson, Arizona. We have significant experience in millimeter wave technology. We've done a lot with radars, radio, software, wireless systems, and we're expert in putting all those systems together to make a complex system. So that's just a brief of who we are. And so next, we want to just say where we are today with our products. So we feel that we have a novel approach, including IP around antennas, system architecture, noise figure, and to get high power. We have a modular design in order to support global frequency rollout. So our prototypes at this time are at 28 gigahertz, but we have the ability to change that to any frequency. We also have modularity in our output power. And we also have a lot of experience with cost reduction via ASIC creation with both the RF, analog, and digital domains. So that's going to be a key factor in getting the cost down. We have functional prototypes in hand. We have 5G millimeter wave repeaters and the components. We're starting field testing now, and we're working to prep units for FCC compliance testing, and we're engaged with carriers, and we're in conversations with a variety of industry players in order to get a strategy around putting this into the commercial market. So then what makes us different? So we're primarily focused on non-phased array solutions for the millimeter wave 5G marketplace. So one of the key elements of that is a dual polarized polyrod antenna with variable gain and beam width. And Kevin Patrick, our CTO, will be talking about that later on in the talk, showing you some pictures and some simulation results. And so what are the features and benefits? So one of the things that we do is that we connect the transmit and receive antennas directly to the power amp and the low noise amp. So in doing that, we get a very high transmit power and efficiency, because we spend a lot of effort getting the high power up at the millimeter wave frequencies, and we don't want to waste that with switches and loss after that power generating element. And the same thing on the receive side, we have a nice low noise amplifier. We want to get that antenna connection as close as we can to the low noise amplifier. And the other item is that the antennas, we have a very consistent unit-to-unit performance, and it's a very low-cost approach. Kevin will cover some of the details of our low-cost approach. So we're going to show some examples today with repeaters and also a multi-directional antenna system. Okay, repeater basics. So the purpose of this chart, I'm going to introduce a couple terms that we use here, and then also just talk about the physics of the wave propagation. So if we have a source, reading the source over there on the left-hand side of the chart, and we have the equation for space loss there down at the bottom. So if you go 1 kilometer, you get 121.4 dB of loss. And if you let that wave continue to propagate onto 2 kilometers, you only incur another 6 dB of loss for a total of 127.4 dB. Now, if you intercept that wave at the midpoint there at the 1 kilometer point, and you retransmit that signal, now you're starting that wave all over again, and you incur another 121.4 dB of path loss getting to the 2 kilometer point. So now we have a 242 dB loss versus the 127, so that's 115 dB more, and basically the repeater subsystem has to make up for that loss. And then here you see in the center we have a donor unit and a service unit, so a DU and an SU. So the donor unit typically points towards the GNB, and that typically has a higher gain antenna. And then the service unit is a lower gain antenna because it has a broader beam width to cover a larger area. And so that, just want to introduce those terms. We're going to be using DU and SU throughout the talk here. So here are some performance analysis results showing some of our typical specs that we have on our repeater, and the primary focus of this chart is to show that there's a range of solutions when you start talking about distances from the GNB to the DU and then the SU to the UE, and we're looking at signal to noise ratio on the y-axis, and that's kind of our figure of merit there. And then on the x-axis, we have the repeater to UE range in feet. And then each of the lines there, each of the colored lines, is the GNB to DU distance. So you can see as you go up in distance that once you get to 40,000 feet, the repeater didn't have sufficient gain. So all the lines that pretty much coalesce onto the same line, that's showing that the repeater had sufficient gain in order to achieve a output power. And then when we fell short of gain, then those lines start to separate from one another. So you can see there, so looking at the downlink on the left, we can get a pretty good range with a decent signal to noise ratio. So look at the 20,000 foot mark. We're just under 20 dB signal to noise ratio at 1,000 feet from the UE to the repeater. But then if you go to the uplink, that same line, you're just above 0. So it's showing that you're going to be limited by your uplink, because the UEs have a much lower power and a much lower antenna gain. So it's just showing that there's a range of solutions here, and basically the specs I have for the repeater are the same in both cases, except one is uplink, one is downlink. Okay, moving on to 4G versus 5G millimeter wave repeater challenges. So just want to point out some of the challenges here with moving to the higher frequency range. So the operational frequency is about 40 times. The bandwidth is about 10x. And all of the millimeter wave repeaters are TDD, which means the uplink and downlink frequencies are the same, whereas in FDD they use different frequencies. And so using the same frequencies, it increases the likelihood for oscillations. And the biggest thing is the space loss. So we have in terms of just looking at a loss at a one kilometer, there's 120 to 124 dB per kilometer free space loss. versus 88 to 100 dB for the lower frequencies. And that basically means that you're going to get 10 to 64 times less range in free space, not including the poor building penetration. And we know a lot of what we're dealing with here is going to be, blockages. But there are cases where we are just going on free space loss. And I think that is the end of my little section here. So next up, we're going to have Marwan Krunz talking about why we're using 5G millimeter wave repeaters and some of the use cases.
Joel, just if I can ask a couple of questions before we let you go, and also
Sure.
a couple of comments have been, maybe you're moving the PC around or you're moving something around, but now and again there's a bit of fade as if the mic is just farther away from the person speaking. But
Okay.
I'm sure you can handle that. It's just maybe something going on. Anyway, if I could ask just a couple of questions briefly, and then we'll let you carry on. First
Sure.
one is from Tom. He said the SNR versus distance plot is based on what modulation and data rate?
Right. So the reason why we did the SNR, so it's just a pure SNR, so you could pick the modulation and data rate based on that signal to noise ratio. That was the idea behind that plot.
Okay.
Hope you don't understand, and if it's not, we could take that offline later.
Okay, so Tom, if you want to take that in more detail, let us know, and we'll try and answer that for you. And as Ricardo said, he's also there to answer any questions live or afterwards as well. Second question from Eric Leclerc from UMS. He says he'd like to know if you could cover something about the 26, which is the European, and the 28 gigahertz bands with the same line, or do you need to split solutions? And then there's also a question came in on a similar topic saying, main trends for 5G millimeter wave in terms of combining 28s and 39 gigahertz. Is that something you can just talk about briefly?
Yeah, so moving to the different frequency bands, the antenna bandwidth, so that would be a different unit. So it would be basically the same architecture. We would just change antennas. A lot of the electronics probably could cover the 26 gigahertz band, so it would just be a matter of changing the antenna for covering the different frequency ranges. So right now we don't have a solution that does both frequency ranges simultaneously at this point.
Okay, all right. A couple more questions if I can, just before you carry on. Comment here: millimeter wave in 5G usually line of sight. Is that correct? So your repeaters will have to be line of sight for a repeater to function, is the question.
Yes.
Yeah. Okay. All right. And let me see. One more for you. Oh, no, that was the one. Okay. So I'll let you carry on. Thanks very much, guys.
Okay, Graham. Thank you.
Hi everyone, this is Marwan Krunz, the 5G Chief Scientist for ED2. And just maybe before I get into the use cases for 5G millimeter wave repeaters, just to comment on one of the last questions about the SNR thing. We did, the ability to get a particular modulation. Associate a particular SNR with a modulation scheme is receiver dependent. So we did not want to necessarily, we wanted to, to be more generic and just display the SNR versus distance based on the measurements that we obtained. But just a quick comment on one of the questions. Let me just get into, maybe take this a little bit to a higher level. First of all, for those of you who are maybe not necessarily into the repeater space, why 5G repeaters? Why 5G millimeter wave repeaters? Repeaters did exist for a while. They've been used always for 3G, 4G, and others. But the case for 5G repeaters is even much stronger. In the case of millimeter wave, primarily due to the non-uniformity of the capacity of millimeter wave. And there are different fronts to that. One is the fact that, at these high frequencies, you get lots of obstructions. Line of sight is the primary source of the signal. Maybe in some cases you get some reflections, but typically you don't get rich scattering that would enable you to get a strong signal. On top of that, in rural and sparse areas, there's very limited 5G coverage. So repeaters come here to fill a gap in terms of coverage, to be able to extend the reach or the high capacity of 5G millimeter wave to areas where maybe operators are not willing to, spend, high expenditures and deploy GMBs to achieve uniform 5G coverage. So, with that in mind, I mean, we kind of targeted these very, several use cases, both urban as well as rural areas, for different configurations of our repeaters. Maybe kind of a related thought here is, we're talking about extending, high capacity through repeaters. But as many of you are aware of, 5G is not only about broadband, but it's also about low latency and ultra reliability, especially for kind of mission critical applications. And repeaters may still basically need to support some of these applications. So in terms of basically the ability to switch signals at very high speeds and with very low latency in support of these applications. So this is kind of a chart of the three main use cases that the 5G community and by extension repeaters will have to kind of take into consideration when supporting or when extending or boosting the signal beyond the range of a GMB. Okay, so let me zoom in and maybe talk a little bit about the repeaters that we've been working on here at ED2. And maybe, if I may highlight the main, most relevant features here in terms of the EIRP. Right now we are able to achieve a minimum of 51 dBm EIRP in these repeaters. At the same time, simultaneously, very, very efficient receive sensitivity. We use something called the effective isotropic sensitivity factor, which is basically the noise figure minus the receive antenna gain as a metric of interest here, showing how effective, how efficient the repeater performance is. We've been demonstrating so far. We've demonstrated 64 QAM, but extrapolating the results, we see that we can get up to about 2.5 kilometer. At the highest possible QAM, 256. This is still actually to be kind of validated, but 64 is really what we have measured with our repeater. If you lower the QAM, the modulation order, you can achieve a much longer range. In fact, you can reach up to 12 kilometer with maybe a QPSK signal. So, and Kevin later on will talk about the antenna, the high antenna gain technology, very disruptive technology that does not rely on phase shifters and that has, low cost, symmetric features that makes it a very appealing for 5G millimeter wave repeaters. So, this is kind of high level highlights of all the repeater configurations we have. But the repeaters can be used in different use cases. So we are considering here 3 different configurations for different use cases. One is intended as a range extension repeater, primarily for rural areas, to achieve to kind of cover, to fill coverage gaps where LTE 5G signals may not be even present, or very weak faint signals. So these require kind of a range extension. So that's kind of one brand of repeaters that we have. And as Joel mentioned earlier, such repeaters have two parts: a donor unit and a service unit. The ERP is, as I mentioned earlier, at a minimum of 51. This is for the DU pointing towards the GMB. The electronic gain that combine the DU and the SU, the electronic gain without any antenna gains, we are achieving now 90 dB with a very high range. And the antennas themselves, we have different forms of antennas, and that you can trade off the form factor of the antenna with the gain. So, but the ones that we're working with can be around 20 dBi gain, especially the ones that are pointing towards the GMB. And later on, you'll hear more about the dual polarized operation for on these antennas, both the V and H polarization. So the next configuration of repeaters, a little bit. I mean, they share certain, many aspects of the previous one, but here the configuration is a bit different in terms of the connectivity. These are intended for urban environments where you basically have non-line of sight scenarios. You need to bend the signal around the corner. So the key aspect of these what we call them ACR repeaters is that the signal coming from the GMB will have to be split into different directions. So there will be multiple service units that are connected to a hub to the donor unit. They're still actually served by the same reference frequency, so this, all the units are being synchronized. The system uses, the high band frequency, that is collected at the DU, is basically down converted to IF below 6 gigahertz. Then it, at the SU, it's up converted back again and retransmitted. Last but not least, and this is somewhat, maybe the more involved use case, which is the outdoor to indoor, where the donor unit sitting outside is feeding several SUs, maybe one per floor. These SUs are all connected again through a hub and all cabled to the donor unit. There are kind of more specific issues to dealing with the indoor-outdoor environment than the other repeaters, but maybe we can get to that into a later point. But the configuration is, as you see here in the figure, basically that the DU would be looking, having a fixed beam, directional narrow directional beam towards the GMB and taking the signal, feeding it into multiple SUs, for example, in a building situation. Okay, with that, I'm going to, maybe let Kevin get into more details about the specific technologies and the antennas that we use for our repeaters.
Okay, Marwan, again, can I just ask a couple of questions just before we carry on with Kevin?
Sure.
Excellent. Okay, first one that's just come in from Darshan. Do we lose multi-user MIMO gain with repeaters? Are there challenges with quality of service and issues when you think about 911 location identity, things like that?
So in order to support MU MIMO, it depends on, are you talking about 2x2 MIMO, for example, in which case we don't, you don't lose it. If you're going to, higher order MIMOs, the repeater itself is agnostic to the specific waveform. So whatever is happening at the digital domain is going to be, it will be transparent within the repeater. Right.
Okay. Because that was another question. Is it transparent, or do the repeaters have
waveform agnostic for the time being?
Okay. Okay. Next question: is the repeater operating model 1 of broadcast? I'm not sure.
Say that again.
Yeah, is the repeater operating at model 1 of broadcast?
Broadcast.
Yeah, I'm not sure what it means either, actually. So, Ray, if you want to just re-ask that question in case we don't quite understand that question. Okay, and in that case, can I just move on to a couple of other questions for you? Can you comment with regards to sort of pros and cons with regards to integrated access and backhaul, because that's one of the areas I know some of our friends have been looking at that. So, you know, what are the carriers? If you've been talking to any carriers, what do those guys think about in that area? Because we know they've been quite interested in that. If you could just have a comment perhaps on that.
Well, I can't comment on what carriers are saying, but I can tell you, I mean, you know, IAD versus repeaters, I mean, there are subtle differences in here. Right now, we're looking at repeaters as boosters, as signal boosters, without necessarily, you know, decoding and retransmitting signal. Although there might be some plans in the future to do other things. But for the time being, again, for cost purposes, I mean, repeaters do have a big advantage over IAD, because of the fact that they are primarily, you know, amplify and, you know, retransmit kind of, you know, technology. So there's no decoding of, you know, there's no digital decoding at this point in repeaters.
Okay. And talking of carriers, I got a couple of questions from carriers actually. One of them is how many beams from the donor site can be utilized by the repeater?
How many beams? The configurations that you've seen so far is there's a single beam. Now that beam could be, and maybe later on you'll see some, you know, something that corresponds to that answer. This could be one of several possible beams. We don't do any, you know, beam forming in the sense of steerable. We don't do like electronic steerable antennas. So typically there would be one beam from the DU pointing towards the GNB.
Okay.
But with both polarizations, obviously.
All right. Okay. Thank you. And the next question from a carrier was, are millimeter waves, because you mentioned earlier that the different use cases with 5G, specifically interested in, you know, whether or not millimeter wave repeaters would be suitable for example, in factories, for the, you know, the new use cases that are being discussed, where a very reliable millimeter wave connection is needed for ultra reliable low latency connections.
Is this like, I guess is the question is in the context of outdoor to indoor? I mean, kind of looking at factories with lots of sensors and devices, IoT devices being collected and, you know, going because I think that might fall under the indoor to outdoor type of repeater. Okay.
All right. Well, listen, rather than taking too much time on it now, that came from a guy from Vodafone, so I'm sure we can follow up on that later on. Okay, so thanks very much, Marwan. Let's see what Kevin has to tell us.
Thank you, Tom.
Okay, I'm Kevin Patrick, and I'll be talking about some of the technology and innovations that we come up with for our repeaters. So first of all is the type of antenna we're using. We don't use a phased array antenna like most of the technology companies are doing. We use basically a polyrod antenna. It's kind of like a dielectric waveguide antenna. It can be adjusted to have a wide beam or a narrow beam, so high gain, low gain. The actual concept was developed by Bell Laboratories way back in 1947, so it's not actually a new concept at all. It's just that that's the technology that we just chose to go with for our particular repeater. The nice thing about it is it's a very efficient type antenna because we don't have to split the signal to go to multiple patches or any of that kind of stuff. Where you might have to put maybe even an amplifier between each patch in a phased array, or a combining or dividing network that might have to be done. We don't do that, so we basically get all the energy to and from the antenna from our circuitry. By adjusting the length of that polyrod, you can change the gain. Likewise, by changing the gain, you also are changing the beam width. So by just changing the length of the polyrod, you get different gains and different beam widths. And our design is incorporated so that we can actually change the antenna out in the field if necessary to be able to get a different gain or a different beam width as if necessary, or as the scenario requires for the different locations of our repeaters in the field. Our repeater that we had, our antenna that we have, we came up with, the first iteration was a helix-based circularly polarized antenna at 28 gigahertz. We decided to then change to a dual polarized linear type antenna to get both vertical and horizontal polarization. And we also developed a lower cost technique so that the antenna wasn't a very high cost for the repeater. And I'll show you what that kind of looks like in the next couple slides. Polyrod antennas also, the nice thing about them is you can point them in different directions, as long as you're not pointing them in the same direction, they basically don't change the characteristics, beams, and so on of the adjacent polyrod in a configuration, which I will actually show in pretty much the last slide that we have. So the polyrod antenna is basically a dielectric rod antenna. A figure of it, our circular polarized version, is on the left there, and it has a very symmetric beam that comes out of it. This is our simulation of the beam, and we actually have some anechoic chamber testing that was done by a third party for us. A polyrod antenna could be either linear, circular, dual polarized, both linear or circular. It can be done however you want. The actual rod is just focusing the beam in whatever in a straight direction from the active element, essentially. We can switch between polyrods in our systems in basically nanosecond timing. This is basically what we used for our dual polarized antenna. This is the design of it. It's a 21-layer printed circuit board. We bond the dielectric rod, polyrod, to the printed circuit board, and it's, like I said, it's field replaceable. It's connectorized. You just unscrew it from the unit on the inside, replace it with a different gain or beam width antenna, and away you go. It's like I was saying, it's a very symmetric design because of the symmetry of the actual rod itself. You get both the E and the H beam width is almost identical to each other. It's very repeatable from antenna to antenna because of the fact it's a printed circuit board technology. So there's no tuning involved, nothing like that. You build it up and away you go. It has excellent cross-pole isolation. The plots below show that the main beam has a gain of about 19.5 dB, and the side lobe gain of the cross pole is on the order of around minus 10.911 dB. That's off axis. On axis, the cross pole isolation is in excess of 40 to 50 dB, so we get excellent cross pole isolation for the need for the system requirement for cross pole isolation. Some of the challenges for millimeter wave transmission on printed circuit boards is you want to have a very low cost product. So printed circuit board techniques are kind of mandatory for this. You don't want to use cabling where you're trying to put connectors on stuff. So everything is a printed circuit board technology and surface mount components. Some of the challenges you have with a printed circuit board is inboard isolation between paths, isolation between the paths through the air. So you have to take great care into making sure that no higher order modes or any modes are transmitted either through the printed circuit board where they're not supposed to be going, or through the air above the printed circuit board. So you have to have housings that restrict the radiation from one circuit to another. You have to put mode suppression vias inside the printed circuit board to prevent transmission of the wave inside the printed circuit board between the layers of the board. You also want to take, and we discovered that you want to keep everything basically on the surface of the board. Anytime you go into the board with vias, that's just basically a radiating antenna inside the printed circuit board. So we restrict that. We restrict cavity sizes to make sure that the cavities are waveguide below cutoff. You also have to worry about power supply isolations from one circuit to another. Say they're both working on a 5-volt power supply, two different circuits. You don't want the signal, the RF signal, being transmitted through the power supply from one, say, amplifier to another amplifier. Those kind of things cause oscillations and so on. So we've come up with great techniques and care to make sure that we have tremendous isolation in the printed circuit board itself. One of the things we discovered was routing of the transmission lines. The first time we made one of the boards, we discovered that we were getting a loss of about 1.3 dB per inch at 28 gigahertz. That was unacceptable. We came up with a technology or a technique to greatly improve that loss, lower the loss in the transmission line. Our final version ended up being about 0.6 dB per inch. So, you know, creating a gain inside the unit and then losing it in transmission lines is not, you know, a good thing to do. So we come up with a way to solve that problem, and it's working very well for us. Also, we have, because of the fact that the system is TDD, it's good to be able to switch amplifiers on and off. One of the big problems is our high power amplifier. It operates at 20 volt DC with quite a bit of current. So switching that amplifier on and off could be quite a problem, since the amplifier requires large capacitive values to keep the amplifier itself stable, to prevent it from oscillating and so on. So we came up with a circuit that greatly improved and reduced the time it takes to switch, say for instance, that high power amplifier on and off. We got actually numbers better than 750 nanoseconds, because that was our goal. This is actually what we came up with. When we originally built the circuit, we were having a switching speed of around 10 microseconds. Very unacceptable. So then we tried to improve it. We got it down to 2.4 microseconds switching speed. Our final ended up being less than or about 400 nanoseconds. So we greatly improved the switching speed of that high power amplifier. So now we can do power management to reduce the overall power dissipated by the unit, along with preventing possibly transmitter and receiver feedback oscillations. So this was a great thing that we actually came up with to reduce the switching speed. Another problem we had when we were going into making repeaters was components. There's a lot of components out there, but not much at the millimeter frequencies that we are working at. So we looked into it. A lot of them, filters were very expensive, high loss. So we thought, well, let's see if we can reduce the cost of our filters and come up with ones that are actually smaller and better for our particular needs. So we decided to design our own filters, and they're available on Avnet and DigiKey website. So you can actually purchase these filters. You can see by the diagram off to the right, that's a 2.9 millimeter connector, and right next to it is actually the filter mounted on a test board, so you can actually get these and test them. So the filters themselves are very small and low cost. We also had the problem with our antenna, you know, trying to get an antenna. That's why we actually ended up making our own, because trying to purchase something like that was literally almost impossible. So we made our own antenna. Another product that we actually have that could be used for a repeater is this multi-directional unit. It's an array of amplifier modules with antennas mounted to each module, both receive and transmit. It's very modular. You can replace each one of those sections with a new module that would work at, say, a different frequency, at 26, 24, 39, whatever the case might be. So it's very modular. You can also make it so that you can receive the signal, say, for instance, from the GNB with a very high gain antenna, and then have lower gain broad beamwidth antennas to distribute the signal around say, a neighborhood or a small community, maybe even inside of a stadium or something like that. So it's switchable. The technology we use inside the unit does not reduce the power out of each one of those antennas, or reduce the noise or increase the noise figure that we're getting on the received portion of it. So any signal that goes into the unit gets transmitted out of each antenna that it goes to at full power or at the optimum noise figure. We don't degrade anything by going out of this. This was a unit that we actually produced for a third party that wanted something like this. So this is another one of our units. It also has a small, the small view off to the side lower right corner there. It can send a signal in a long direction out with a very narrow beam width for long, long distance coverage. And then for the close area around this particular unit, you could put either a narrow beam antenna or a wide beam lower gain antenna for the coverage around the actual unit. And we can switch these antennas in and out within fractions of microsecond down into the nanosecond range. And this is all done without any phased array or phase shifting. So you don't have to have a calibrated unit for phase shifters or any of that kind of stuff. That basically concludes our presentation. And for any information you want, you can contact Ricardo Platt, who he's been mentioned before, for any other questions after this presentation.
And yes, we do have a lot of questions. I'm going to try and just cover everything if I can. Question, I mean, because as you know, some of the installation engineers, that you have a different set of engineers depending on power. Some people are able to do stuff when it's at low power. They have to get other guys in to do it if it goes above a certain power limit. And I think that's variable across different countries. So are we looking at the US at the moment with this, or are you looking globally?
Right. Right now we're actually looking in the US, but we have contacts in other countries, neighboring countries. So we are working with them also for repeaters.
Okay, all right. If I can just keep going down this list of questions. So the question here is, how's beam management handled, like around the corner or when a UE is moving? Or is this, I guess, a fixed wireless type use case that you see this for?
Right. So if you have the repeater, we can set it up so that it either has a broad beam where people can move around within that beam, or go from beam to beam. The typical repeater that we have only has one beam output. So as long as you're staying within the beam, you shouldn't have a problem for mobility. The long distance ones, to go possibly for multiple hops or something like that, could have a narrow beam going from repeater to repeater. The actual unit set up in the field would, that would be adjusted for that particular scenario need.
Okay, and I think you may have answered this when you were talking about the antennas, but how do you adjust antenna orientation, especially on the donor side?
So you actually have to, because of the fact that our antenna is fixed inside the unit, you basically point the donor unit at the GNB. So it would be a field setup.
Okay, And again, I'm just reading these questions if it's okay, guys. So, and the repeater, how does it tackle isolation when you've got, do you shift frequencies to try and cut out any electromagnetic isolation issues?
Right, a lot of that is proprietary that we have, but we're getting in excess of, in some cases, better than 120 dB of isolation between circuits. So, yeah, can't get into that too specifically.
Okay, I mean, you could always pick up on these guys afterwards. You'll have the data from who's asked these questions.
Right.
How's the PA connected to the antenna? Is a question then. There's a few mechanical questions coming up.
Right, so the actual antenna is connectorized with very low-cost connectors, and the amplifier's on the main printed circuit board with, so there's only a fraction of an inch between the amplifier and the antenna element.
Okay, and again, I think you may have answered this earlier. Can the antenna be adjusted remotely or electronically, or does it require manual adjustment?
It requires a manual adjustment.
Alrighty. So question here in terms of the practical bandwidth of polyrod antennas.
Right, we're getting in excess of a gigahertz. I think we're actually getting more like 2 or 3 gigahertz of bandwidth out of it.
Okay, and another question on the what type of PCB and what type of dielectrics are being used?
It's standard printed circuit board material. We're not using exotic materials like ceramic or quartz glass or anything like that, but we have been looking into possibly using those other materials for other applications of this antenna.
Okay. The polyrods seem to be quite long. Do they stick out of the repeater, and if so, how strong are the polyrods?
No, they all are confined inside. Like for instance, if you look at this particular unit, it shows that the polyrods are sticking out of the unit. This is without the radome attached to it, so you wouldn't see any of the polyrod. They are relatively strong, but they could break if you really, bend them.
Yeah.
But that shouldn't be the case. And in our repeater, they're all encased inside the unit.
What is the typical impedance of such polyrod antennas?
They're matched a 50 ohm system.
The question of dimensions of the antenna electrical length.
The electrical length is multiple wavelengths, and there's actually articles that you can get online to see how polyrods actually work.
Okay. Are we using SIGI technology for PAs or something else?
The power amplifier that we're using right now is currently a GaN technology.
Right. So I understand a single beam can be enough from the repeater to the GMB. However, how do you direct the beam from the repeater to the UEs, which may be located in different places?
Right. So right now we're using, if the UEs are in a fairly close proximity to the repeater, we would use a broad beam antenna, or the possibly this type of unit here, where we could switch the beams between different sectors around the repeater itself. If it's a long distance, then we use a narrower beam antenna, higher gain.
All right. One of the comments that was made earlier about the Release 16 IAB getting some sort of favor with network operators now. Do you see that as being I don't know, a risk to the opportunity here, because that's offering, I guess, greater opportunities in some ways than repeater technology, or do you see this as being a separate play?
This is Marwan. I think the issue here is a cost issue. I mean, one of the biggest advantages of repeaters over GNBs is really the additional cost per subscriber. If you go to an IAB kind of technology and you have to go on kind of digital domain, so clearly the cost is going higher. So, I mean, clearly both are possible options and probably advocated, but we don't necessarily think that from a cost perspective, I think repeaters are going to always have an advantage.
Well, once again, big thank you to our friends from ED2.